Hello, my name is Nikolaos Kouteloulis, and I'm an active researcher in wind power integration for more than 20 years now. And my present position is professor in offshore wind grid integration at the Technical University of Denmark in Denmark. And in the promotion project, I was the principal investigator from GTU and also acted as a work package leader for work package 3, in which capacity I was, of course, also a member of the project management group. My presentation today concerns work package 3 in promotion, the wind turbine generator and converter interaction, a work package where I will try to give you an introduction to the work we've done here, what were the objectives, why we were doing what we were doing, and maybe pass you the main messages of the work package before you are welcome to move on and look at the individual presentations that go more into details of the different technical aspects. But in principle, work package 3 was aiming at de-risking the diode rectifier based HVDC transmission for offshore wind, and by doing that it had to develop grid forming control solutions for offshore wind power plants. And while we were at it, since we had these grid forming control solutions, we also looked at black start from offshore wind power plants. The project, the work package was had a number of partners. I think I will start again here, starting now. So work package 3 had a large number of partners that comprised of a number of universities, but also significant industrial presence from wind turbine manufacturers to power equipment manufacturers to developers, TSOs, and bodies which are working into standardization and certification. And as already said, the main focus of the work package was on diode rectifier as offshore HVDC unit. And as you might also know, that the typical way of building offshore wind connected to shore via HVDC transmission today is by having a voltage source converters, typically an MMC converter offshore, and then the connection to the shore. By employing a diode rectifier unit, what we are basically doing is replacing this main unit as VSC unit with a diode rectifier unit, which can be smaller and more distributed than this one. And of course, by doing that, or we started looking at that because the expectation was that it could provide significantly lower cost for the offshore transmission of wind power. Now, having a diode rectifier unit is not something new. It's something that has been around for many years. So one might ask, why is there a big issue when if you want to replace the offshore VSC converter with a diode rectifier unit? Well, this is the case because in normal conditions, and what I call normal conditions is by having a VSC HVDC converter offshore, this converter is the one that is creating and maintaining the offshore AC network voltage and frequency. In this case, the wind turbines, all they have to do is connect to this AC network and then operate as grid following wind turbines, meaning that they are trying to inject active and reactive power into the grid and be synchronized with the voltage and the frequency that is created in the grid. But by replacing the VSC converter with a diode rectifier unit, we are losing the capability, the control capability. The diode rectifier unit is a non-controllable unit, so we are losing these capabilities, which means that somebody else should generate the offshore voltage and frequency. And in this case, the only other units available offshore are, of course, the wind turbines. And in this case, the wind turbines should not only try to inject active and reactive power into the network with their main scope of producing power, which will be transmitted to the shore, but then they should also generate and maintain the voltage and the frequency on the AC network. That will mean that the wind turbines are moving from grid following wind turbines straight to grid forming wind turbines, and this is a very new paradigm and a very new operating mode for the wind turbines. We used to say it's a fundamentally different way of controlling the wind turbines. So in order to do that, the work package, this, as I said, maybe the individual units of the individual units were not anything new in the system, but the whole system is something new. So the work package had the objectives to first define the functional requirements, so what the offshore wind farms should be able to do, and it should be controlled. So if they are connected to a diode rectifier unit, then actually develop test cases and control algorithms to test these functional requirements. And since once we do that, we should also look at how this would do the compliance evaluation. And after do all these things, then inside the project also provide recommend grid code requirements for such an operation. And as I said, we did all those things, those 4 objectives, but during the lifetime of the project, black start came up as one of the main topics. So we extended this work to do the same for black start, where pretty much the similar steps were followed. So the objectives was define functional requirements, develop test cases and control algorithms, define and apply compliance evaluations, and finally recommend the grid code requirements. Now, before you move on to watching the rest of the videos, which will go into the technical details of the work and present the results, I would like to bring you the main messages for work package 3. So first of all, grid forming operation is possible for wind turbines, and we've tested that both in a scenario where they are connected to diode rectifier transmission unit, but also when we are looking at self-energization and black start operation. So trying to energize also the onshore network. And for DRU transmission is technically feasible and achievable. I think the work package has managed to provide to de-risk the technology by doing extensive simulations. We defined requirements, we verified compliance and provided recommendations, and we also paved the way to the laboratory demonstration that was done in the promotion project in work package 16. When it comes to self-energization and black start operation, I think is the same, technically is feasible. There we have different options of doing that. It could be a hard switch or a soft start, and each one of them has advantages and disadvantages. But in this case, the grid forming control needs to be also robust to the large changes that we find in the grid resonant peak, and also to be robust to the interactions with other converters and generators in the area. And not least, of course, fault recovery is important in all operation modes or in all concepts and configurations, but in the case of black start operation, it's even more important when we have a large number of grid forming wind turbines, generators, or wind power plants. So with that, I think I will just introduce you or tell you that we have published a large pool of deliverables with the results of the different stages of the work, and you can find them all on for download on the promotion webpage. But also we have a long list of scientific publication where it's also available there. So between these publications that you can find and read anytime you want, and the presentations, the video presentations that are following, I hope you will get a very good and detailed impression and information about the work we are doing. And just to very briefly tell you that the rest of the presentations are, the video presentations are related to DRU connected offshore wind power plants, and then on the black start part we have a couple of presentations. And finally, we have a number of industrial partners which will present how they see the results from their industrial perspective and discuss about future steps and exploitation. So enjoy your reading and your watching the videos. Thank you very much. And before I stop, I would like to remind you that we will have the live webinar on 4th of September, and I will be present together with my colleagues, and we will be glad to interact with you with any questions you may have. Thank you.